The cosmic context. Why do we look for life beyond our stars? Could life exist beyond our stars? With billions of galaxies brimming with planets, the odds favor a universe teeming with civilizations, waiting to be discovered. Human fascination with the stars dates back thousands of years, but only in the last few centuries have we developed the tools and theories to seriously consider the possibility of life beyond Earth. The vast, cold space of space seems hostile at first glance, but with each new discovery, we come closer to answering the age-old question: are we alone? We know that our solar system is just one of potentially billions of others scattered across a universe that began with the Big Bang approximately 14 billion years ago. This massive event created everything we know: the galaxies, the stars, the planets, and all the elements that form the building blocks of life. As the universe expanded and cooled, stars began to form, and with them planets formed. Among these countless worlds, Earth became a unique oasis of life. But could she really be the only one? A crucial step in our intellectual journey to find life beyond Earth came in 1961, when astronomer Frank Drake formulated what became known as the Drake equation. This seemingly simple formula attempts to estimate the number of civilizations in our galaxy that we could potentially communicate with. The equation takes into account factors such as the rate of star formation, the proportion of those stars with planets, the number of planets that could support life, and so on. Although the equation does not provide a definitive answer, it serves as a framework for the scientific community. Despite its broad assumptions, the Drake equation suggests that the universe could be teeming with life, provided certain conditions are met. And as our observation techniques improve, we are beginning to understand how many of these conditions might exist outside our solar system. But for all the optimism that the Drake equation inspires, there is an equally sobering puzzle posed by Italian physicist Enrico Fermi. If the universe is so vast and ancient, and if life is likely to emerge on other planets, where is everyone? This question, known as the Fermi paradox, highlights a troubling reality. Despite decades of searching, we have yet to find clear evidence of extraterrestrial civilizations. Some scientists suspect that this lack of contact may be due to the so-called Great Filter principle, a critical stage in the evolution of life that is extremely difficult to overcome. This could mean that although life often emerges, it almost always fails to reach the stage of developing advanced technology. Alternatively, it could be that we have already passed the Great Filter, and intelligent life is simply rare, leading to long periods of cosmic silence between civilizations. In recent decades, however, we have made monumental progress in identifying planets outside our solar system, called exoplanets, that could potentially support life. The Kepler Space Telescope, launched in 2009, revolutionized this field by discovering planets through the transit method, which measures the dimming of a star's light as a planet passes by it. Kepler alone has identified thousands of exoplanets, some of which lie in the so-called habitable zone of their parent stars, where liquid water could exist. The habitable zone, often called the Goldilocks zone, is the area around a star where the temperature is just right, not too hot, not too cold, for liquid water to exist. Liquid water is crucial because it is a fundamental solvent for the chemistry of life as we know it. One such exoplanet is Kepler 22b, discovered in the year 2011. This planet orbits its star within the habitable zone and is about 2.5 times the size of Earth. Although we don't yet know whether Kepler 22b has an atmosphere or whether it could support life, it is a tempting candidate for further study. With advances in telescope technology, including the upcoming James Webb Space Telescope, which will allow us to study the atmospheres of distant planets in more detail, our search is only beginning. Webb is designed to detect chemical signatures in the atmospheres of exoplanets, gases such as oxygen, methane, or carbon dioxide that could indicate the presence of life. Of course, it is possible that life exists in forms very different from what we know on Earth. On our own planet, life thrives in extreme conditions, from the icy depths of Antarctica to the searing hydrothermal vents on the ocean floor. These extremophiles suggest that life could potentially arise in a variety of environments that may seem inhospitable to us. Consider the moons in our own solar system, such as Europa and Enceladus. Beneath their icy surfaces, these moons likely hide oceans of liquid water kept warm by gravitational forces that generate internal heat. If life can exist around hydrothermal vents on Earth, it stands to reason that similar environments on Europa or Enceladus could also support microbial ecosystems. NASA's Europa Clipper mission, scheduled to launch in the mid-1920s, aims to investigate this possibility by exploring Europa's ice-covered ocean. As if the potential for life in our universe wasn't enough, some scientists speculate that our universe may not be the only one. The multiverse hypothesis suggests that there could be an infinite number of universes, each with its own physical laws. If this is true, it would greatly expand the possibilities for life, as some of these universes may have far more favorable conditions for life than our own. However, the multiverse hypothesis remains highly speculative and lacks direct observational evidence. Nevertheless, it reminds us that the boundaries of our knowledge are constantly being expanded by theoretical physics, and our understanding of the cosmos is probably far from complete. The vastness of space may seem like an insurmountable barrier in our search for life beyond our planet, but we are at the beginning of an exciting era of discovery. As our technology improves and our understanding deepens, we will continue to search the stars for signs of life, be it microbial or intelligent. In the next chapter, we'll delve deeper into the specific scientific discoveries that have fueled hopes of discovering life elsewhere, from the discovery of potentially habitable exoplanets to the exploration of the icy moons of our own solar system. The stars may seem distant, but the search for life beyond our planet is closer than ever. The ingredients of life, what we need to find in the cosmos. To understand the search for life beyond Earth, we must first understand the fundamental ingredients that make life possible. At the most basic level, life as we know it requires 3 key elements: water, energy, and complex carbon-based chemistry. These components form the foundation for all living organisms on Earth, from the simplest bacteria to the most complex plants and animals. However, our exploration of the cosmos has led to the realization that life may not be strictly bound to these conditions. In this chapter, we will examine the known requirements for life and alternative possibilities, as well as astronomical discoveries that suggest these ingredients may be present on other worlds. Water is often called the universal solvent because it is capable of dissolving more substances than any other liquid. This ability is crucial to enabling the chemical reactions that sustain life. On Earth, wherever there is liquid water, we also find life. It's no wonder that when searching for potentially habitable planets or moons, scientists pay particular attention to whether there is water there. But why is water so special? Water's unique molecular structure allows it to dissolve a wide variety of chemicals, making it the ideal medium for biochemical reactions. Additionally, water remains liquid over a relatively wide range of temperatures, enabling life in environments as diverse as deep hydrothermal vents in the oceans and icy glaciers. Across our solar system, the search for water has taken us to surprising places. Mars, for example, was long considered a dry, barren planet. But in recent years, NASA rovers have discovered evidence of ancient riverbeds and minerals that can only form in the presence of liquid water. In the year 2018, the European Space Agency's Mars Express orbiter discovered a vast underground lake beneath the planet's southern ice cap. Although this water is probably very salty, there is a possibility that microbial life could exist in Mars's subsurface aquifers. However, the icy moons of Jupiter and Saturn are even more promising. Europa, one of Jupiter's largest moons, is thought to have a global ocean beneath its frozen surface. The Galileo spacecraft that orbited Jupiter in the 1990s provided convincing evidence that Europa's subsurface ocean may be in contact with the moon's rocky mantle, creating conditions similar to Earth's hydrothermal vents where life thrives. Meanwhile, Enceladus, a moon of Saturn, is ejecting water vapor and organic compounds into space, suggesting that an ocean of liquid water also lies beneath its ice layer. These moons are tempting targets for future missions. NASA's Europa Clipper and Dragonfly missions, scheduled for the mid-1920s, will explore Europa and Saturn's largest moon, Titan. Titan is unique in the solar system in having lakes and rivers of liquid methane and ethane on its surface. Although methane and ethane are not water, their presence in liquid form suggests that life could exist in a form completely different from anything we have ever known. The second ingredient for life is energy. All organisms need a source of energy to power their metabolic processes. On Earth, this energy comes primarily from two sources: the sun, which drives photosynthesis in plants, and chemical reactions that support life in environments where sunlight does not penetrate, such as the deep hydrothermal vents of the oceans. When searching for extraterrestrial life, scientists look for planets or moons that are close enough to their star to receive sufficient energy, but not so close that they will be burned by intense radiation. These habitable zones are also known as Goldilocks zones, where the conditions are just right for liquid water to exist, and energy to be available in usable quantities. The discovery of locked rotating planets, planets that always face the same side of their star, has complicated the search for life in the Goldilocks zone. These planets could have one side that is extremely hot and another side that is freezing cold, with a narrow strip of temperate conditions in between. However, newer models suggest that atmospheric circulation could help distribute heat, which could make these planets more habitable than originally thought. One such planet is Proxima Centauri b, located just over 4 light-years away in the habitable zone of the closest star to our Sun. In addition to starlight, many moons and planets in our solar system also get their energy from another source: gravitational interactions. Jupiter's immense gravity exerts a strong tidal force on its moons, particularly Io, Europa, and Ganymede, creating internal friction that heats their interiors. On Io, this leads to constant volcanic activity, while on Europa, the subsurface ocean remains liquid beneath the ice layer. Similarly, Enceladus also experiences tidal heating through its interactions with Saturn, which may drive hydrothermal activity on the seafloor of its ocean. This tidal heating phenomenon opens the possibility of habitable environments far from a star's traditional habitable zone. It even suggests that planets and moons orbiting gas giants could harbor life even in the icy outer regions of a star system. Carbon is the backbone of all known life forms because it has the unique ability to form stable, complex molecules. Carbon atoms can form bonds with up to 4 other atoms, allowing the formation of long chains and complicated structures such as proteins, lipids, and nucleic acids, the building blocks of DNA and RNA. When searching for life beyond Earth, scientists look for environments rich in organic molecules, compounds made up mostly of carbon and hydrogen. The discovery of organic molecules on Mars, Enceladus, and Titan has raised hopes that these places could harbor or once harbored life. What might life look like without carbon? Although carbon is the basis of life on Earth, it is theoretically possible that other elements could play a similar role in extraterrestrial life forms. An alternative would be silicon-based life. Silicon, like carbon, can form 4 chemical bonds and is abundant in the universe. However, silicon-based compounds tend to be less stable than their carbon-based counterparts, especially in the presence of water, which is why silicon-based life is considered less likely. Another interesting possibility is that life could exist in solvents other than water. On Titan, for example, the methane and ethane lakes and rivers could support chemical reactions that are completely alien to our understanding of biology. In 2015, NASA scientists proposed that azotosomes, membrane-like structures made of nitrogen, hydrogen, and carbon, could form in liquid methane, potentially creating a stable environment for life. Atmospheres play a critical role in protecting life from harmful radiation, regulating surface temperatures, and creating stable environments in which complex chemistry can take place. In addition to protecting us from ultraviolet radiation, Earth's atmosphere traps heat, preventing the planet from completely freezing. This greenhouse effect, fueled by gases like carbon dioxide and methane, is critical to maintaining temperatures that support life. When searching for habitable planets, scientists look for atmospheres that can perform similar functions. Venus and Mars are both close to the inner and outer edges of the Sun's habitable zone, but their atmospheres have made them uninhabitable. Venus, with its thick carbon dioxide atmosphere, is experiencing a runaway greenhouse effect that keeps surface temperatures high enough to melt lead. Mars, on the other hand, has an atmosphere too thin to support liquid water on its surface. For exoplanets, the composition of the atmosphere can be inferred by studying the light filtered through the atmosphere as the planet passes in front of its star. This technique, known as transmission spectroscopy, allows scientists to detect the presence of gases such as oxygen, methane, and carbon dioxide, gases that could indicate biological activity. In 2018, for example, the Hubble Space Telescope discovered water vapor in the atmosphere of K2-18b, a super-Earth located 111 light-years away. When searching for life, scientists look for biosignatures, chemical compounds, or physical processes that could indicate the presence of living organisms. On Earth, oxygen is a key biosignature produced primarily by photosynthetic organisms such as plants and algae. Methane, produced by both biological and geological processes, is another potential sign of life. Detecting oxygen or methane in an exoplanet's atmosphere could be a strong indication that life exists there. However, these gases can also be produced by non-biological processes, such as volcanic activity or chemical reactions with surface minerals. Therefore, detecting a combination of gases that are not in equilibrium, such as oxygen and methane together, would be a more convincing sign of life. While the search for life focuses heavily on detecting microbial organisms or simple ecosystems, the search for intelligent life continues through the efforts of the Search for Extraterrestrial Intelligence (SETI) program. SETI scientists use radio telescopes to scan the sky for signals that could indicate the presence of an advanced extraterrestrial civilization. In 1977, SETI researchers discovered a powerful, narrow-band radio signal that became known as the WOW signal. Although it lasted only 72 seconds and was never received again, the signal remains one of the most intriguing mysteries in the search for extraterrestrial intelligence. While it is possible that the signal was caused by natural phenomena, some scientists believe it may have been a brief transmission from an extraterrestrial civilization. In recent years, SETI has expanded its search to include laser signals that could be used by advanced civilizations to communicate across interstellar distances. The Breakthrough Listen initiative, launched in 2015, aims to scan the 1 million nearest stars for such signals and search 100 nearby galaxies for signs of technology. Although the search for extraterrestrial life has made significant progress, we are still in the early stages of understanding the complexity and diversity of life that may exist in the universe. It's entirely possible that alien life is so different from what we know that we might not even recognize it if we encountered it. As Carl Sagan once said, "The universe does not have to be in perfect harmony with human ambition." In the next chapter, we will explore the latest discoveries in exoplanet research, focusing on specific worlds that offer the greatest potential for hosting life. From the Earth-like worlds of the TRAPPIST system to the extreme conditions of hot Jupiters, we will examine the planets that could one day become targets of interstellar exploration. The worlds that could harbor life, exoplanets, and their potential for civilizations. As our technology improves and we learn more about the universe, we are increasingly discovering thousands of exoplanets, planets outside our solar system, that could potentially harbor life. These exoplanets have a wide variety of sizes, compositions, and environments. Some are Earth-like and orbit their stars in the habitable zone, while others are gas giants that challenge our understanding of planetary systems. In this chapter, we will explore the most fascinating exoplanets that may harbor life, from Earth-sized worlds to mysterious ocean planets. One of the most promising categories of exoplanets are the rocky, Earth-sized worlds that orbit in the habitable zone of their stars. These planets are often referred to as Earth twins because they share many of the same characteristics as our home world. Although they are not identical to Earth, they are similar enough to raise the possibility that they could support life. In the year 2014, NASA's Kepler Space Telescope made a groundbreaking discovery: a planet about the size of Earth located in the habitable zone of its star. This planet, known as Kepler 186f, lies about 500 light-years away in the constellation Cygnus and orbits a star much cooler and smaller than the Sun. Kepler 186f is only about 10% larger than Earth, making it almost a perfect match in terms of size. What makes Kepler 186f particularly exciting is its location in the habitable zone of its star, where temperatures could allow liquid water to exist on the surface. Its red dwarf star is cooler than our Sun, meaning the habitable zone is much closer to the star. Kepler 186f completes an orbit around its star in about 130 days, about a third the length of an Earth year. However, one challenge with red dwarf stars is that they are known to be extremely active stars. They often emit powerful solar flares that could blow away the atmospheres of nearby planets or expose any life on their surfaces to deadly levels of radiation. Scientists are still debating whether Kepler 186f has an atmosphere thick enough to protect it from such eruptions. Nevertheless, its location in the habitable zone makes it a prime candidate for further study. Much closer to us is Proxima Centauri b, an exoplanet orbiting Proxima Centauri, the closest star to our solar system, just over 4 light-years away. Proxima Centauri b is one of the most promising exoplanets we have discovered so far, not only because of its proximity, but also because it is in the habitable zone of its star. Discovered in the year 2016, Proxima Centauri b is slightly larger than Earth and requires only 11 days to complete an orbit around its red dwarf star. Like Kepler 186f, Proxima Centauri b is likely locked to its star, meaning one side of the planet always faces the star, while the other side lies in eternal darkness. This could create extreme temperature differences between the day and night sides, but scientists speculate that a thick atmosphere could spread heat around the planet, making it more suitable for life. Proxima Centauri b has captured the imagination of many astronomers because it is so close. If we ever sent an interstellar probe to another star system, Proxima Centauri b would likely be the first target. But as with Kepler 186f, the star's activity could pose a problem for the planet's habitability. Red dwarfs like Proxima Centauri are known for their frequent and intense stellar flares, which could sweep away the atmosphere and make the planet less hospitable to life. Future missions, such as the Breakthrough Starshot initiative, aim to accelerate tiny space probes using laser beams to explore Proxima Centauri and its planet. These lightweight probes could travel up to 20% of the speed of light and potentially send back data within a few decades. One of the most exciting discoveries in recent years is the TRAPPIST-A system, located approximately 39 light-years away in the constellation Aquarius. In the year 2017, astronomers announced the discovery of 7 Earth-sized planets orbiting a single, ultra-cool dwarf star. What makes this system particularly intriguing is the fact that 3 of the planets are in the star's habitable zone, where liquid water could exist. The TRAPPIST-A planets are all about the size of Earth and orbit much closer to their star than the planets in our solar system do. The entire system could fit within Mercury's orbit. Because the star is much cooler and fainter than the Sun, its habitable zone is much closer, allowing the planets to maintain relatively mild temperatures even at such short distances. The 3 potentially habitable planets, known as TRAPPIST-AD, TRAPPIST-AE, and TRAPPIST-AF, are of particular interest. These planets may have oceans of liquid water, and their relatively close distances from Earth make them excellent candidates for atmospheric studies with the James Webb Space Telescope. By analyzing the light that passes through their atmospheres during transits, scientists hope to detect the presence of gases such as oxygen, methane, and carbon dioxide, possible indicators of life. Like other red dwarf stars, TRAPPIST-A is vulnerable to stellar flares that could sweep away its planet's atmospheres or expose them to intense radiation. The question of whether these planets can retain their atmospheres despite the eruptions remains the subject of intensive research. Are super-Earths bigger planets with more potential? While Earth-sized planets are exciting candidates in the search for life, there is another fascinating class of exoplanets called super-Earths, planets that are larger than Earth but smaller than gas giants like Neptune and Uranus. These planets could potentially offer thick atmospheres, stable climates, and more area for life to develop. In the year 2015, astronomers discovered an exoplanet often referred to as Earth's older cousin, Kepler 452b. This super-Earth is about 60% larger than Earth and orbits a star similar to our Sun, but much older. Kepler 452b lies about 1,400 light-years away in the constellation Cygnus and is in the habitable zone of its star, where conditions could support liquid water. Kepler 452b takes about 385 days to complete one orbit, making its year very similar to Earth's. Its larger size suggests it may have a denser atmosphere and possibly more active geology than Earth, which could help regulate its climate. However, because its star is much older than the Sun, about 6 billion years, It is possible that Kepler 452b experienced a runaway greenhouse effect in which its surface temperatures became too high for life. Despite these uncertainties, Kepler 452b remains one of the most promising super-Earths in the search for life. Its location in the habitable zone and its similarity to Earth make it an attractive target for further study. Another fascinating super-Earth is LHS A40b, about 40 light-years away in the constellation Cetus. Discovered in the year 2017, this planet is about 1.4 times the size of Earth and orbits a red dwarf star in the habitable zone. What sets LHS apart is its high density, suggesting that it is composed primarily of rock and metal, similar to Earth. LHS's location in the habitable zone suggests that it may have liquid water on its surface, but its higher gravity and denser composition mean that its atmosphere could be very different from Earth's. If LHS retained a thick atmosphere, it could have the necessary conditions to support life, but further observations are needed to confirm this. The James Webb Space Telescope and other upcoming missions will likely focus on planets like LHS A40b to analyze their atmospheres and look for biosignatures. Its relative proximity to Earth makes it an ideal candidate for detailed studies. In addition to rocky, Earth-like planets and super-Earths, there is another category of exoplanets that could harbor life, the so-called ocean worlds. These are planets or moons that have vast oceans beneath their surfaces, which could potentially provide habitats for life in completely different environments than those on Earth. Closer to home, one of the best candidates for an ocean world is Europa, one of Jupiter's 4 large moons. Europa is covered by a thick layer of ice, but beneath that frozen shell lies an ocean of liquid water kept warm by the tidal forces created by Jupiter's powerful gravity. NASA's Galileo spacecraft provided strong evidence for the existence of Europa's subsurface ocean in the 1990s, and subsequent missions have confirmed that this ocean may contain more water than all of Earth's oceans combined. The ocean is believed to be in contact with Europa's rocky mantle, creating the possibility for hydrothermal vents, similar to those found in Earth's oceans, that could provide the energy needed to sustain life. NASA's Europa Clipper mission, launched in 2024, will explore this mysterious moon in more detail. By flying over the surface and using radar to penetrate the ice, the mission will look for signs of habitability and possibly even detect microbial life. Another fascinating ocean world is Enceladus, a small moon of Saturn that has attracted scientists' attention because of the dramatic geysers that spew water vapor and organic compounds into space from the South Pole. These geysers, first observed by the Cassini spacecraft, suggest that Enceladus has a global subsurface ocean beneath its icy surface. Like Europa, Enceladus's ocean is heated by Saturn's tidal forces, creating the possibility for hydrothermal activity on the seafloor. The presence of organic molecules in Enceladus's geysers is particularly exciting because it raises the possibility that microbial life could exist in the Moon's ocean. Future missions to Enceladus will focus on studying these geysers in more detail and looking for biosignatures that could indicate life. As our technology advances, we are entering an exciting new era of exoplanet research. The soon-to-be-launched James Webb Space Telescope will revolutionize our ability to study the atmospheres of distant planets and search for signs of life. Next-generation telescopes, such as the Extremely Large Telescope and LUVOIR, will enable even more detailed observations, allowing us to directly detect exoplanets and analyze their atmospheric composition. In the next chapter, we will look at the implications of the discovery of life beyond Earth. What would it mean for humanity if we discovered even the slightest trace of life on another planet? How would this affect our understanding of biology, our place in the universe, and our hopes for the future of space exploration? The impact of the discovery of life, what it means for science and humanity. The discovery of life beyond Earth would be one of the most profound and transformative events in human history. For centuries, we have wondered whether we are alone in the universe, and the discovery of even the smallest microorganism on another world would fundamentally change our understanding of life, our place in the cosmos, and the potential future of humanity. In this chapter, we will examine the scientific, philosophical, and societal implications of the discovery of extraterrestrial life and consider how such a discovery might change our thinking. If we discovered life on another planet, the immediate question would be, how similar or different is it compared to life on Earth? Biologists have long debated whether the principles of life on Earth, such as the use of carbon-based molecules, the need for liquid water, and the reliance on DNA or RNA to carry genetic information, are universal. Would life on another planet follow the same rules, or could it be radically different? Does the origin of life have a common ancestor or a separate origin? One of the first questions scientists would ask is whether the discovered life has a common origin with life on Earth. For example, if we were to discover microbes on Mars, we would need to figure out whether they evolved independently or are related in some way to life on Earth. This could happen through a process known as panspermia, in which life, or the building blocks of life, is transported between planets by comets, meteorites, or other space debris. If Martian life shares biochemical similarities with life on Earth, such as using the same amino acids or nucleotides, this could indicate that both planets were populated from the same source, perhaps an asteroid impact billions of years ago. Alternatively, if Martian life turns out to be completely different from life on Earth, that would mean that life in our solar system arose independently more than once, which would significantly increase the likelihood of life throughout the universe. Another question would be, what kind of environment supports this life? Life on Earth exists in an astonishing range of environments, from the scalding waters of hydrothermal vents to the freezing deserts of Antarctica. These organisms, known as extremophiles, thrive in conditions that would be fatal to most life on Earth. If we discovered life on a planet or moon with extreme conditions, like Europa's icy oceans or Titan's methane lakes, it could expand our understanding of where life can exist. It would also give us new insights into the resilience of life and the adaptability of biological systems. Life in these extreme environments could teach us more about the potential for life on planets far outside the traditional habitable zone. Consider the philosophical implications of this simple question: are we alone? The discovery of extraterrestrial life, even in its simplest microbial form, would have profound implications for philosophy, religion, and human self-understanding. For millennia, humans have seen themselves at the center of the universe, either literally, as in the ancient geocentric models, or metaphorically, as the only known intelligent life. Finding life elsewhere would force us to reconsider our place in the cosmos. The Copernican revolution in the 16th century fundamentally changed our understanding of the universe. When Copernicus proposed that the Earth revolved around the Sun, it downgraded humanity from the center of the cosmos to just another planet orbiting a star. The discovery of extraterrestrial life would be a similar paradigm shift, but on a much larger scale. As Carl Sagan often pointed out, the realization that we are not the center of the universe is a humbling experience. Finding life elsewhere would remind us that the universe was not made for us, and that we are just a small part of an incredibly vast and ancient cosmos. It would also suggest that life is not a rare event, but a common result of the laws of physics and chemistry. This shift in perspective could have profound effects on how we view ourselves and our role in the universe. What are some of the theological implications? What do religions say? Religions around the world have long grappled with the possibility of life beyond Earth. Many religious traditions assign humanity a special role, often as the pinnacle of creation, or as the only beings created in the image of a god. The discovery of extraterrestrial life, particularly intelligent life, could challenge these beliefs. Some theologians argue that the discovery of life beyond Earth would not necessarily contradict religious teachings, but would expand the scope of creation. Christianity, for example, might interpret extraterrestrial life as part of God's creation, with humans still playing a unique role. Islam also teaches that Allah is the creator of all worlds, and the existence of life on other planets would only confirm this belief. In contrast, some religious traditions may have difficulty reconciling the existence of extraterrestrial life with their teachings. For example, if an intelligent alien species had developed its own religions or ethical systems, this could raise questions about the universality of religious principles that are often considered absolute on Earth. The Fermi paradox asks, why haven't we heard of other civilizations? The discovery of even microbial life on another planet could reignite debates around the Fermi paradox. The question of why, given the vastness of the universe and the apparent likelihood of intelligent life, we have not yet discovered signs of advanced civilizations. If life is common in the universe, why haven't we heard of anyone? There are many possible answers to this paradox. One possibility is that life is common, but intelligence is rare. It could be that microbial life arises relatively easily, but the development of complex, intelligent life is much more difficult. Alternatively, intelligent civilizations could exist, but they do not use the communication technologies we expect, or they intentionally avoid contact with us, a scenario known as the zoo hypothesis. The discovery of microbial life would suggest that life can arise under a variety of conditions, but it would not necessarily answer the question of why we have not yet discovered intelligent life. In fact, he may deepen the mystery of the Fermi paradox by pointing out that while life is common, advanced civilizations are extremely rare or have chosen not to interact with us. What social and cultural impact would this have? How would humanity react? Beyond the scientific and philosophical implications, the discovery of extraterrestrial life would have profound effects on human society. How would people react? Would it inspire fear or hope? Would it unite humanity in the pursuit of knowledge or divide us along political, cultural, and religious lines? Public reaction to the discovery of life beyond Earth would likely be mixed. While many would be excited by the prospect of answering one of humanity's biggest questions, others might react with fear or skepticism. History has shown that people often respond to the unknown with fear, and the discovery of extraterrestrial life, especially intelligent life, could inspire fear of the unfamiliar. In the late 1970s, the Viking missions to Mars, which conducted experiments to detect life, generated great public interest and excitement. Although the results were inconclusive, they demonstrated public interest in the idea of finding life beyond Earth. Today, the rapid spread of information via social media could increase both excitement and fear as people deal with the implications of such a discovery. Popular culture has long primed us for the idea of encountering extraterrestrial life. From the benevolent aliens in E.T. the Extraterrestrial, to the gritty depictions of invasion and conquest in War of the Worlds. These depictions shape public perceptions of what extraterrestrial life might look like and how we should respond to it. If we were to discover microbial life or evidence of an ancient civilization, it would likely evoke a variety of emotional responses, from awe to fear. The political and ethical question is, who owns extraterrestrial life? The discovery of extraterrestrial life would raise a number of political and ethical questions. Who would have the right to explore or interact with extraterrestrial life? Would countries cooperate in the search, or would they compete for the prestige and economic benefits of such a find? International space law, as codified in the Outer Space Treaty of 1967, declares that outer space is the common property of humanity, and no country can claim sovereignty over extraterrestrial bodies. However, this treaty was written before the discovery of exoplanets and the serious consideration of extraterrestrial life. As private companies and nations develop the ability to explore and potentially colonize other planets, these laws may need to be revised. Ethically, the discovery of life on another planet raises questions about how we should interact with it. Should we protect alien ecosystems from contamination, similar to how we protect endangered species on Earth? If we find microbial life on Mars, should we stop human exploration to avoid disturbing its environment? These questions are becoming increasingly important as our exploration of the solar system advances. One of the most optimistic views on the discovery of extraterrestrial life is that it could unite humanity. As Carl Sagan once said, looking at Earth from space, the pale blue dot, reminds us of the fragility and interconnectedness of all life on our planet. The discovery of life elsewhere in the universe could reinforce this sense of unity and remind us that we are all part of a larger cosmic family. The search for life beyond Earth transcends national borders, political ideologies, and cultural differences. It is a truly global undertaking, requiring collaboration between scientists, governments, and private organizations from around the world. If we were to discover extraterrestrial life, it could serve as a reminder of our shared humanity and inspire greater cooperation to address Earth's challenges, such as climate change, resource scarcity, and conflict. What does the future hold for the search for life? As we look to the future, the search for life beyond Earth is entering an exciting new phase. Technological advances, such as the James Webb Space Telescope and next-generation observatories, will allow us to study the atmospheres of distant planets in unprecedented detail. Missions to Europa, Mars, and other promising worlds in our own solar system will continue to search for signs of life, both past and present. At the same time, the development of new propulsion technologies could bring interstellar exploration within reach. Concepts like Breakthrough Starshot, which aims to send tiny laser-powered space probes to nearby stars, could allow us to explore exoplanets like Proxima Centauri b within a human lifetime. As we continue to explore the cosmos, the question of whether we are alone in the universe remains one of the most fascinating mysteries of our time. Whether we find microbial life on Mars, detect biosignatures in the atmosphere of a distant exoplanet, or receive signals from an advanced extraterrestrial civilization, the discovery of extraterrestrial life would change humanity forever. In the next chapter, we will examine the future of human space exploration, from plans to colonize Mars to the possibility of interstellar travel. What challenges must we overcome to become a spacefaring civilization? And what role might extraterrestrial life play in our journey beyond Earth? The future of humanity in space, colonization of other worlds, and the path to interstellar species. The discovery of life beyond Earth would revolutionize our understanding of the universe, but it also raises questions about humanity's future in space. As we continue to explore the cosmos, there is growing interest in expanding humanity's presence beyond our home planet. From plans to establish colonies on the Moon and Mars to long-term visions of interstellar travel, humanity is on its way to becoming a spacefaring civilization. In this chapter, we will examine the challenges, opportunities, and implications of colonizing other planets and consider what it would mean to travel beyond the stars. In recent years, Mars has emerged as a prime target for colonization efforts. While the Moon provides a nearby testing ground for technologies and strategies, Mars opens up the potential for a sustainable human settlement. With its day-night cycle, seasons, and subsurface ice, Mars is more Earth-like than any other planet in the solar system, making it the logical next step for human exploration. Why Mars? What is the potential of the red planet for colonization? Mars provides a relatively stable environment for human exploration. Its day, only slightly longer than Earth's, provides a familiar rhythm for human settlers. The planet also has polar ice caps and large amounts of subsurface water ice that could be used to sustain life and support missions. Mars is also the most intensively researched planet after Earth. Since the mid-20th century, space agencies have sent over 40 missions to the red planet, providing detailed information about its surface, atmosphere, and history. NASA's Perseverance rover is currently exploring the surface of Mars, looking for signs of ancient life and collecting samples that could one day be brought back to Earth for analysis. While Mars is far from a perfect replica of Earth, it may well be possible to establish a permanent presence there. The key will be to create self-sustaining habitats that can support long-term human life. Is terraforming on Mars science fiction or a future reality? For many, the ultimate goal of Mars colonization is to turn it into a second Earth. This process, known as terraforming, involves changing a planet's environment to make it habitable for human life. The most ambitious version of terraforming would involve creating a denser atmosphere, increasing surface temperatures, and introducing liquid water to the surface. Currently, Mars has a very thin atmosphere made up mostly of carbon dioxide, offering little protection from harmful radiation. To terraform Mars, scientists would need to find ways to increase the planet's atmospheric pressure and temperature. One proposed approach is to release carbon dioxide trapped in the planet's polar ice caps to thicken the atmosphere and create a greenhouse effect. This could increase temperatures and potentially allow liquid water to exist on the surface. However, optimistic estimates suggest that terraforming Mars would take centuries or millennia. While the idea is popular in science fiction, it may be more practical to focus on creating self-sufficient habitats on Mars that can support human life in the near future. These habitats could use local resources like water to sustain life without requiring a complete redesign of the planet. Colonizing another planet, be it Mars or a more distant world, presents a variety of technical, logistical, and ethical challenges. The harsh conditions of space, vast distances, and the need for sustainable resources present significant obstacles to long-term human habitation. One of the biggest challenges people face in space or on other planets is radiation exposure. On Earth, we are protected from harmful cosmic and solar radiation by our atmosphere and magnetic field. Mars, on the other hand, has no such protection, exposing potential settlers to dangerous levels of radiation. Long-term radiation exposure can increase the risk of cancer and damage genetic material, which is a major problem for space exploration. Microgravity is also a challenge for space travelers. While Mars has about a third of Earth's gravity, living in low-gravity environments for extended periods of time can have serious health effects, including muscle loss and loss of bone density. Scientists are currently researching ways to mitigate these effects, such as through artificial gravity habitats or regular exercise programs. Beyond the physical challenges, space exploration also presents psychological challenges. Isolation, confinement, and the long distances between the settlers and the Earth could have a negative impact on mental health. Life on Mars or any other planet would require advanced psychological support systems and social structures to ensure settlers' well-being. In order for a colony to survive on another planet, it must become self-sufficient. This means that it relies on in situ resource utilization, the practice of using local resources to support human life. On Mars, for example, settlers could extract water from ice deposits and use the planet's carbon dioxide-rich atmosphere to produce oxygen and fuel. Food production is another crucial aspect of colonization. In the near future, settlers might rely on supplies from Earth, but in the long term, they would have to grow their own food. Experiments on the International Space Station have shown that it is possible to grow crops in space, but scaling agriculture on Mars will require significant technological advances. Researchers are exploring the possibility of using hydroponics or aquaponics, systems that grow plants without soil, to provide food for future Martian colonies. While Mars is the focus of current colonization efforts, it is not the only place in the solar system that could support human life. The moons of the outer planets, particularly Europa and Enceladus, have emerged as interesting candidates for future exploration and possible colonization. These moons are thought to host oceans beneath their surface that could provide the water and energy necessary to support life. More opportunities for colonization? Europa, one of Jupiter's largest moons, is covered by a thick layer of ice beneath which lies a vast ocean of liquid water. The Galileo spacecraft provided strong evidence for the existence of this ocean in the 1990s, and recent missions have confirmed its existence. The prospect of liquid water makes Europe an exciting destination for future exploration. While the moon's icy surface would pose challenges for human habitation, scientists speculate that geothermal activity at the bottom of Europa's ocean could provide energy and create environments similar to Earth's hydrothermal vents where life thrives. NASA's Europa Clipper mission, launched in 2024, will study the moon's habitability in more detail. Saturn's moon Enceladus is another potential candidate for future exploration. Like Europa, Enceladus has a subterranean ocean of liquid water beneath its icy surface. The Cassini spacecraft discovered geysers that eject water vapor and organic molecules into space from the moon's south pole, suggesting the ocean may contain the necessary ingredients for life. Although Enceladus is much smaller than Mars or Europa, its oceans and organic chemistry make it a fascinating target for astrobiology. Future missions could examine Enceladus's geysers for signs of life and explore the potential for human habitation in the distant future. While colonizing the solar system would be a monumental achievement, the ultimate goal for many space visionaries is interstellar travel, the ability to travel beyond our solar system to other stars. Such travel is currently far beyond our technological capabilities, but scientists are already exploring concepts that could make interstellar travel a reality in the coming centuries. The biggest challenge of interstellar travel is the immense distance. The closest star system, Proxima Centauri, is over 4 light-years away. At the speed of our fastest space probes, it would take tens of thousands of years to reach it. To make interstellar travel feasible within a human lifetime, we would need propulsion systems that could reach a significant fraction of the speed of light. Several concepts for advanced propulsion systems are currently being investigated, including nuclear fusion, antimatter propulsion, and laser-powered space probes. Launched in 2016, the Breakthrough Starshot Initiative aims to develop tiny, laser-powered space probes that could travel to Alpha Centauri in just 20 years. These lightweight probes would be powered by lasers on Earth and could reach speeds up to 20% of the speed of light. Another possibility for interstellar travel is the concept of generation ships, giant spaceships that would house multiple generations of people during the journey to another star. These ships would function as self-sufficient ecosystems, with life support systems designed to sustain human life for centuries or even millennia. Alternatively, some scientists have suggested using cryosleep, the process of freezing astronauts to revive them upon arrival at their destination. While this concept is still in the realm of science fiction, advances in cryonics and medical technology could one day make it possible. The human urge to explore. Why we reach for the stars. As we complete our journey through the possibilities of life beyond Earth, we are left with a fundamental question. Why do we as a species feel so strongly driven to explore the universe? What drives humanity to venture into the unknown, whether in search of extraterrestrial life or to understand our place in the universe? In this final chapter, we will examine the historical, philosophical, and psychological reasons behind our drive to explore space and the future of human search for the stars. The human desire to explore is not new. Throughout history, humans have been driven by curiosity and the pursuit of discovery. Be it the early migration from Africa, the exploration of the oceans, or the space race of the 20th century, humanity has always strived to go beyond the limits of the known. The age of discovery, which began in the 15th century, offers important parallels to modern space exploration. Back then, European explorers set sail across unknown oceans, driven by the promise of new trade routes, riches, and the desire for knowledge. These explorers faced many of the same challenges that today's space explorers face: vast distances, hostile environments, and the need for sustainable resources. Just as explorers of the past searched for new lands, today's scientists search for new worlds. The discovery of exoplanets, particularly those in the habitable zone, has revived the spirit of discovery. While we may no longer seek new continents, we are exploring new frontiers in the cosmos, places where humanity could one day live and thrive. The mid-20th century saw the beginning of the space race, a period of intense competition between the United States and the Soviet Union for dominance in space exploration. The launch of Sputnik 1 in 1957 marked the first successful artificial satellite, and just over a decade later, the United States landed the first humans on the Moon with the Apollo 11 mission. The space race was driven by political and military motives, but also reflected the human desire to explore beyond Earth's boundaries. The moon landing showed that humanity was capable of reaching new frontiers. It was a moment of collective success, not just for the United States, but for all of humanity. Today, we stand on the threshold of a new era of space exploration. Governments and private companies are working together to return people to the moon, explore Mars, and even explore the possibility of interstellar travel. Just as the space race spurred technological innovation and scientific discovery, the next wave of space exploration promises to push the boundaries of what is possible. Beyond the practical and scientific reasons, there are deeper philosophical motivations that drive the human drive to explore the cosmos. Space exploration is not just about finding new planets or understanding the laws of physics. It is a search for answers to fundamental questions about existence, meaning, and our place in the universe. One of the deepest motivations for space exploration is the desire to understand our origins. Where do we come from and how did life begin? Are we unique? Or is life a widespread phenomenon in the universe? These questions have fascinated humanity for thousands of years, and space exploration offers the opportunity to find answers to them. The search for life beyond Earth is part of this search for knowledge. Even the discovery of a single microorganism on another planet would provide profound insights into the conditions necessary for the emergence and development of life. But it would also raise new questions. If life can exist on Mars, Europa, or in the atmospheres of distant exoplanets, what does that mean for the universality of life? How common are the processes that led to the emergence of life on Earth? Space exploration also allows us to understand the broader history of the universe. By studying distant galaxies, remnants of ancient stars, and cosmic phenomena like black holes and dark matter, we can reconstruct the story of how the universe came to be. This gives us a better understanding of the forces that shaped our world and the cosmic events that led to the formation of stars, planets, and life. Our search for meaning. What is humanity's place in the universe? In addition to understanding our origins, space exploration forces us to ask questions about our purpose and our place in the universe. Are we alone, or are there other civilizations that may be far more advanced than us? If we find intelligent life, how will it change our understanding of humanity's role in the cosmos? These questions touch on some of the deepest philosophical and religious ideas about existence. Many cultures and belief systems have long believed that humanity has a special place in the universe. The discovery of extraterrestrial life, especially intelligent life, would challenge these views and force us to reconsider our place in the cosmic order. Some philosophers and scientists have speculated that the search for life beyond Earth is partly a search for meaning. If we find that life is common in the universe, It could suggest that life is a fundamental feature of the cosmos, and that we are part of a much larger biological community. However, if we find that life is extremely rare, it could reinforce the idea that life on Earth is precious and unique, with humanity playing a special role in the unfolding history of the universe. What lies behind the thrill of discovery? The unknown has always fascinated humanity. From the depths of the ocean to the distant stars, we are drawn to the mystery of what lies beyond. Space, with its vastness and complexity, represents the ultimate unknown. Each new discovery, be it a distant exoplanet, a black hole, or an unexplained cosmic phenomenon, brings us closer to unraveling the universe, but also opens up new mysteries. This urge for discovery is one of the main motivations for space exploration. The possibility that we might find something truly extraordinary, be it life on another planet, a new law of physics, or a cosmic event we have never seen before, is driving scientists, engineers, and researchers to push the boundaries of what is possible. What awaits us in the future of space exploration? The 21st century is shaping up to be one of the most exciting periods in the history of space exploration. With the rise of private space companies, new government initiatives, and technological advances, humanity is on the threshold of a new era of discovery. One of the most significant developments in recent years is the rise of commercial space travel. Companies like SpaceX, Blue Origin, and Virgin Galactic are pioneering new ways to make access to space more affordable and accessible than ever before. These companies have ambitious plans, from sending astronauts to the Moon and Mars to creating space tourism opportunities for the general public. The idea of establishing human settlements on other planets, especially Mars, is no longer just science fiction. Both NASA and private companies have plans to send humans to Mars in the coming decades, with the goal of creating sustainable habitats where people can live, work, and thrive. While colonizing other planets in our solar system is an achievable goal in the next few centuries, the ultimate dream remains traveling to other star systems. Interstellar travel is one of the greatest challenges humanity has ever faced, but it also represents one of the most exciting prospects for the future. As discussed in the previous chapter, concepts such as breakthrough starshot and generation ships offer potential solutions to the challenge of interstellar travel. If we can develop the technology to travel to other stars, we could one day reach distant exoplanets and explore the possibility of life beyond our solar system. Interstellar travel would open a new frontier of human exploration, opening up the possibility of discovering new worlds, civilizations, and ways of understanding the universe. As we look to the future, one thing is clear: humanity's journey into space has only just begun. The cosmos is vast, mysterious, and full of possibilities. Whether we are searching for life on distant planets, exploring the outer reaches of the solar system, or contemplating the possibility of interstellar travel, we are driven by the same fundamental desire: to understand our place in the universe. Space exploration is more than just a scientific endeavor. It reflects who we are as a species. It represents our innate curiosity, our drive to push boundaries, and our ability to imagine a future beyond Earth. As we continue to explore the cosmos, we will not only learn more about the universe, but also more about ourselves. In the words of Carl Sagan, somewhere something incredible is waiting to be discovered. It is this sense of wonder and possibility that will continue to inspire humanity on its journey to the stars. The Kardashev scale, measuring civilizations in the cosmos. When it comes to thinking about the possibility of advanced civilizations beyond Earth, scientists often use a model to imagine what such civilizations might look like. One of the most famous and convincing models is the Kardashev scale, developed by the Soviet astrophysicist Nikolai Kardashev in 1964. This scale classifies civilizations based on their energy consumption and provides a way to conceptualize the technological advancement of extraterrestrial civilizations. The first level of the Kardashev scale, Type 1, refers to a civilization capable of harnessing and storing all of its home planet's available energy. This includes solar energy, geothermal energy, wind energy, and other forms of energy that are naturally present on the planet's surface. In Kardashev's original definition, a Type 1 civilization is capable of using about 10 to the power of 16 watts. Currently, humanity is far from reaching Type 1 status, but we are moving towards it. Physicist Michio Kaku estimates that humanity is currently at about Type 0.73 on the Kardashev scale. At our current rate of energy consumption, we could reach Type 1 status over the next few centuries, possibly in the 23rd or 24th century. This progress requires not only the full use of all renewable energy sources, but also a fundamental shift in our approach to energy production and sustainability. To achieve Type 1 status, a civilization would have to manage planetary resources in a way that does not harm the environment. In other words, an advanced civilization that consumes energy on a planetary scale must also develop technologies and systems that prevent environmental collapse. This includes mastering climate control, energy efficiency, and even large-scale geoengineering projects to deal with natural disasters, such as hurricanes and earthquakes. A Type 2 civilization would be exponentially more advanced than a Type 1 civilization and capable of harnessing the full energy output of its star. Kardashev estimated that such a civilization would need to control about 10 to the 26 watts of energy, 10 billion times the energy consumption of a Type 1 civilization. How could a Type 2 civilization achieve this? One theoretical possibility is to build a Dyson sphere, a gigantic structure that surrounds a star and captures its energy. This idea, first proposed by Freeman Dyson in 1960, imagines a swarm of satellites or solar panels orbiting a star to collect and store its energy. Building a solid sphere around a star is beyond our current technological capabilities, but a Dyson swarm consisting of thousands or millions of individual satellites could theoretically be achieved by a highly advanced civilization. The discovery of a Dyson sphere or swarm would be one of the most exciting discoveries in the search for extraterrestrial intelligence. Some astronomers speculate that if we find a star that is inexplicably dim or has strange energy patterns, it could indicate the existence of a Type 2 civilization that uses such a structure. One candidate that has caught astronomers' attention is Tabby's star, also known as KIC 462852, which exhibited irregular dimmings that some interpreted as a possible indication of a Dyson swarm. However, recent studies suggest that the darkening is caused by dust or other natural phenomena. A Type 3 civilization represents the ultimate goal of the Kardashev scale, a civilization capable of controlling and harnessing the energy of an entire galaxy. This would require an unimaginable 10 to the 36 watts of energy, which includes the energy of billions of stars. Such a civilization would have technologies so advanced that they would be able to travel throughout the galaxy, colonize planets, harness the energy of black holes, and possibly even manipulate the fundamental forces of physics. In popular culture and science fiction, Type 3 civilizations are often portrayed as godlike beings with nearly unlimited power and knowledge. They might potentially be able to alter space and time, create artificial worlds, or engage in stellar engineering, that is, altering stars to suit their needs. One of the most fascinating questions is how we might discover a Type 3 civilization. If such civilizations existed, they would likely leave behind massive energy signatures, such as waste heat from vast cosmic structures or artificial manipulations of star systems. Some researchers believe that the search for techno-signatures, evidence of advanced technologies, could one day reveal the existence of such civilizations. While Kardashev's original scale ends at Type 3, some scientists and futurologists have speculated about what civilizations beyond this level might look like. A Type 4 civilization could theoretically harness the energy of the entire universe, manipulating dark matter, dark energy, and even the fundamental forces of nature to its will. Such a civilization would likely operate on a scale beyond our grasp, perhaps existing outside of time and space as we understand it. A Type 5 civilization, on the other hand, could have completely transcended the universe and may be multidimensional beings or able to travel between universes in the multiverse. Although these ideas remain purely speculative, they illustrate the unlimited potential for advanced civilizations in the cosmos. In the next chapter, we will examine how extraterrestrial civilizations, whether Type 1, 2, or 3, might interact with humanity and what possible consequences such contact would have for technology, culture, and the future of both civilizations. First contact, how we might communicate with advanced civilizations. If the universe is filled with civilizations of varying levels of technological advancement, the question remains, what would happen if we made contact with one of them? The idea of first contact has long been a central theme in science fiction, but as our search for extraterrestrial life intensifies, it has become a serious scientific consideration. In this chapter, we will examine the different ways that first contact could occur and what the potential outcomes of such an event could be. One of the biggest obstacles to contacting extraterrestrial civilizations is the enormous distance between stars. Even the closest star, Proxima Centauri, is more than 4 light-years away. So any message sent at the speed of light would take over 4 years to reach its destination, and another 4 years to receive a response. For more distant stars, the wait could be centuries or even millennia. Given these timescales, communication with distant civilizations would likely resemble a slow, methodical process, exchanging messages across generations. So some scientists have suggested using interstellar beacons, powerful radio or laser transmitters that can send messages over long distances. The Search for Extraterrestrial Intelligence, SETI, project has long focused on detecting such signals, although no clear contact has yet been made. Another possibility is that alien civilizations use technologies that we do not yet understand. For example, they could communicate through quantum entanglement, a phenomenon in which particles remain connected over vast distances, or even through the manipulation of space and time themselves. If their technology is far more advanced than ours, they could use methods of communication that we cannot currently detect or understand. How could we understand them? How would we decipher their language and culture? Assuming we receive a message from an alien civilization, one of the biggest challenges would be understanding their language. How do you communicate with a species that may not share any of the same cultural, biological, or cognitive frameworks as humanity? Even on Earth, translating languages can be difficult when cultures have little in common. With an alien species, these challenges would be exponentially greater. Some scientists have suggested that mathematics could serve as a universal language. Since the laws of mathematics are constant throughout the universe, a message conveying basic mathematical principles such as prime numbers, geometric shapes, or physical constants could be understood by any intelligent species. In fact, this approach was used in the Arecibo message, a radio message broadcast in 1974 directed at the star cluster M13. The message contained information about the human race, Earth's position in the solar system, and fundamental elements of our biology, all encoded in binary form. However, if civilization is much more advanced than us, its ideas about mathematics, physics, or reality itself could go far beyond our understanding. The difficulty would be comparable to teaching quantum physics to a small child, but potentially multiplied by a completely different biology and way of thinking. What might a first contact scenario look like? There are many ways that first contact could occur, each with its own implications. The most likely scenarios include: this is the most common scenario studied by SETI researchers. We discover a signal from a distant star system that indicates the existence of an advanced civilization. This signal could be a targeted message or a byproduct of their technology, for example, the waste heat from a Dyson sphere. In this case, communication would likely be slow, with decades or centuries between messages. An advanced civilization could send robotic probes to explore the galaxy. These probes could be designed to search for intelligent life and transmit messages to their creators. Some scientists have speculated that Oumuamua, the interstellar object that passed through our solar system in 2017, may have been such an alien probe, although this remains highly speculative. The most dramatic scenario would be the direct arrival of an alien spacecraft in our solar system. If an advanced civilization is able to travel faster than light, or use some other form of interstellar propulsion, they could visit Earth in person. This scenario is less likely due to the enormous energy requirements of such travel, but it remains a possibility in the realm of speculative science. An advanced alien civilization could send us not biological beings, but sophisticated artificial intelligences, AIs, capable of surviving the rigors of space travel. These AIs could act as messengers and mediate communication between our species. Collaboration or conflict? The outcome of first contact depends largely on the nature of the extraterrestrial civilization. Are they peaceful explorers, or are they more interested in conquest and exploitation? Do they see us as equals, or are we just an interesting curiosity to them? If alien civilization is far more advanced than ours, it is possible that they may not even consider us worthy of direct interaction, much like we consider ants or bacteria. In this case, they could observe us from a distance or avoid contact altogether, perhaps to prevent cultural contamination or interference with our natural development. This idea is central to the so-called zoo hypothesis, which posits that advanced civilizations consciously avoid contact with less developed species in order to allow them to develop independently. On the other hand, if the aliens are interested in cooperation, the benefits could be immense. The exchange of knowledge, technology, and culture could accelerate human progress by centuries. Alien technology could enable us to solve pressing global challenges such as climate change, poverty, and disease. It could even open the door to interstellar travel and allow humanity to join a larger cosmic community. However, there is also the potential for conflict. If the alien civilization has a completely different set of values, priorities, or ethical systems, misunderstandings could lead to hostilities. In the worst-case scenario, the aliens could view humanity as a threat or a resource to be exploited. While this is a common theme in science fiction, it remains a real concern for some researchers. In the next chapter, we will explore speculative ideas about post-contact scenarios. What happens after humanity establishes communication or encounter with an advanced alien civilization? How might this change the course of our species? And what are the long-term implications for both civilizations? The post-contact future. How humanity might evolve under the influence of aliens. After the initial excitement of first contact, humanity would face the long-term implications of this new reality. How would our societies, cultures, technologies, and philosophies change if we discovered that we are not alone in the universe? In this final chapter, we will examine the post-contact future and the possible influences of an extraterrestrial civilization on the evolution of humanity. The discovery of extraterrestrial life, especially an advanced civilization, would cause profound cultural changes. As discussed in previous chapters, many religious traditions place humanity in a special, central role in the universe. Realizing that there are other intelligent beings who may be far more advanced than us could challenge these beliefs in ways we don't yet fully understand. Some religious traditions may adapt to this new reality and incorporate extraterrestrial life into their teachings, viewing it as part of a larger divine plan. Others may have difficulty reconciling the existence of advanced alien species with their teachings. The discovery of life beyond Earth could lead to new religious movements or philosophical schools of thought concerned with our place in the cosmos. In addition to religious changes, the existence of extraterrestrial civilizations would likely lead to changes in societal values and priorities. Knowing that we are part of a larger cosmic community could promote greater cooperation between human nations as we unite to understand and interact with these new civilizations. Conversely, it could deepen existing divisions if different groups advocate different approaches to contacting the aliens. One of the most exciting possibilities of first contact is the potential for rapid acceleration of technological progress. An advanced civilization could share knowledge that would revolutionize our understanding of physics, medicine, engineering, and artificial intelligence. Concepts currently beyond our imagination, such as faster-than-light travel, could become reality with the help of extraterrestrial technology. But ethical questions arise about how this knowledge would be used. Would it be distributed evenly across the globe or hoarded by a few? Would alien technology be used to improve the quality of life for all people? Or would it exacerbate existing inequalities? These questions would need to be answered carefully after contact. There is also the possibility that extraterrestrial civilizations could provide us with new sources of energy that could solve many of the environmental problems we currently face. Technologies that use energy more efficiently, such as zero-point energy or antimatter reactors, could enable humanity to move away from fossil fuels and create a sustainable future. The influence of an advanced alien civilization could extend beyond technology and culture to alter human biology and cognition. If we gain access to advanced medical technologies, we could improve our bodies and minds in ways unimaginable today. Genetic engineering, cybernetic enhancements, and the integration of artificial intelligence could allow us to overcome our biological limitations. In addition, extraterrestrial civilizations could have knowledge of biological immortality, i.e., the ability to prevent aging and extend lifespan indefinitely. If humans were to adopt such technologies, it could lead to profound changes in our society, in our relationships, and in our understanding of life. Would we still value the same values if our lifespan were measured in centuries or millennia? There is also the possibility that contact with advanced civilizations could lead to cognitive changes. Engaging with extraterrestrial ways of thinking, languages, and technologies could expand the boundaries of human thought and allow us to understand concepts that are currently beyond our intellectual understanding. Some futurologists speculate that humanity could one day merge with artificial intelligence or even extraterrestrial consciousnesses, creating a new form of hybrid intelligence. Cooperation or conflict in the future of interstellar relations? Once humanity has established contact with an advanced alien civilization, the future of interstellar relations will depend on how both species interact with each other. If the relationship is based on cooperation and mutual respect, it could lead to a golden age of exploration, knowledge sharing, and cultural enrichment. Humanity could become part of a larger interstellar federation or alliance that, together with other civilizations, explores the universe and solves universal challenges. On the other hand, the relationship could be characterized by distrust or competition, which could lead to conflict or even war. The ethical issues surrounding contact with extraterrestrial civilizations are complex, and humanity would need to carefully consider how to deal with this new reality. In the long term, contact with an advanced alien civilization would mark the beginning of a new chapter in human history. It would fundamentally change the way we view ourselves, our place in the universe, and our potential as a species. Whether we evolve into a spacefaring civilization exploring the stars with extraterrestrial partners or remain confined to our solar system, the discovery of extraterrestrial life would be one of the most significant events in the history of life on Earth. As we continue to search the cosmos for signs of life, we are reminded that the universe is vast, mysterious, and full of possibility. The question of whether we are alone has fascinated humanity for millennia, and we may be closer to the answer than ever before. In the end, the search for life beyond the stars isn't just about discovering aliens, it's about discovering ourselves. It challenges us to imagine the possible, to push the boundaries of science and exploration, and to consider what the future holds for humanity as we reach for the stars. Alien megastructures, engineering on a cosmic scale. One of the most intriguing ideas in the search for advanced civilizations is the possibility of alien megastructures, gigantic artificial structures that could span entire star systems. These structures, far beyond what humanity could currently build, would be designed to harness enormous amounts of energy or serve as habitat for entire civilizations. In this chapter, we will examine some of the most compelling theoretical megastructures, how they might be discovered, and what significance their discovery would have for our understanding of intelligent life in the universe. The Dyson sphere is perhaps the most well-known and discussed alien megastructure. Originally proposed by physicist Freeman Dyson in 1960, it is the concept of a civilization building a structure around a star to capture most of its energy. While the idea of a solid, continuous sphere seems unrealistic due to the immense forces involved, a more plausible version would be a Dyson swarm, a collection of thousands or millions of solar-collecting satellites orbiting the star, gradually harvesting energy. A Dyson swarm would allow a civilization to harness astronomical amounts of energy, potentially enough to sustain a Type II civilization on the Kardashev scale. For a civilization that has already mastered planetary energy systems, controlling the energy output of an entire star would be the next logical step. The swarm would provide energy for large-scale projects such as interstellar travel, terraforming, or the creation of vast habitats that could support billions of individuals. Discovering a Dyson swarm could be done by observing stars with unusual darkening patterns. In the year 2015, Tabby's star, also known as KIC 8462852, attracted attention when astronomers observed irregular and significant dips in brightness. While natural explanations, such as dust clouds or exoplanet transits, remain the most likely cause, the idea of an alien megastructure captured the public imagination. If we discovered a star with a clear energy diagram that suggested artificial structures, it would be a strong signal of an advanced extraterrestrial civilization. Another speculative megastructure is the Alderson disk, a theoretical construction that would exceed even a Dyson sphere in scale. Named after science fiction author Dan Alderson, the Alderson disk would be a massive flat disk with a star at the center. The disk would rotate slowly enough to allow gravity simulation on its surface, with the habitable zones located on the disk's inner surface. This structure could potentially house trillions of creatures and provide a nearly infinite surface area for habitation and agriculture. Building an Alderson disk would require technologies far beyond what we can currently imagine, including the ability to manipulate entire star systems and create materials that can withstand the immense forces. But the idea raises fascinating questions about the limits of engineering and the scales at which advanced civilizations might operate. While the Alderson disk concept is purely speculative, it shows the extraordinary potential of extraterrestrial megastructures. Discovering such a structure would likely mean that we are observing a huge, unnatural object blocking or altering the light of its star. If such a megastructure existed, it would be an undeniable sign of an advanced, possibly galaxy-spanning civilization. In Larry Niven's classic science fiction novel Ringworld, published in 1970, the author introduced the concept of a ringworld, a massive artificial ring orbiting a star, with the inner surface serving as a habitable zone. The ringworld would be much larger than any planet and would offer its inhabitants a virtually endless horizon. This idea was inspired by Dyson's work, but focuses on creating a habitable structure rather than just collecting energy. A Niven ring world, or similar ring, would allow the creation of an artificial environment in which entire ecosystems and civilizations could thrive, all within a controlled structure. Unlike a planet which has limited surface area and resources, a ring world could host millions or even billions of Earth-sized biomes, each tailored to the needs of its inhabitants. From an engineering perspective, building a ring world would require immense material and energy resources, as well as the ability to stabilize the structure against the gravitational forces of the central star. A civilization capable of building a ring world would likely be a Type 2 or Type 3 civilization, fully proficient in planetary and stellar engineering. To discover a ring world or similar megastructure, astronomers would have to look for stars with unusual light curves or gravitational signatures. A ring world could block portions of a star's light at regular, predictable intervals as it orbits it, or it could create gravitational anomalies that could be detected by observing neighboring celestial bodies. Perhaps the boldest concept of all is that of the stellar engine, a theoretical megastructure designed to move entire stars across the galaxy. A Shkatov thruster, for example, is a type of stellar thruster that could be used to control the motion of a star by reflecting its light in a direction. This would create a slow but steady thrust, allowing the star, and any planets orbiting it, to move through space. A stellar engine would be the hallmark of a highly advanced Type 3 civilization, capable of manipulating entire star systems to their own ends. One reason a civilization might build such a structure would be to escape catastrophic cosmic events such as supernovae, or to travel across the galaxy in search of new resources and habitable worlds. Over millions of years, a stellar engine could move a star over vast distances and change the shape and dynamics of a galaxy. Detecting a stellar engine would be extremely difficult because a star's movements would occur over incredibly long periods of time. However, if we observed a star that exhibited anomalous motions that could not be explained by gravitational interactions, this could indicate the presence of a stellar engine. Post-biological civilizations, life beyond flesh and blood. When we speculate about the nature of extraterrestrial civilizations, it is important to keep in mind that the civilizations we might encounter may not be biological in the traditional sense. In fact, some scientists argue that the most advanced civilizations may be post-biological. That is, they have made the transition from their organic origins to digital or artificial entities. In this chapter, we will explore the concept of post-biological life, its possible emergence, and what it means for the future of intelligent beings in the cosmos. The idea that biological life could give way to machine intelligence has been explored extensively in both science fiction and serious scientific discussion. As civilizations evolve, they may reach a point where the limitations of biology, such as mortality, susceptibility to disease, and dependence on specific environmental conditions, become barriers to further progress. In response, these civilizations could develop advanced artificial intelligence, AI, that surpasses biological cognition. If AI systems are capable of self-replication and self-improvement, they could quickly surpass their biological creators in intelligence, creativity, and problem-solving abilities. Such AIs could be designed to live indefinitely, resist damage from radiation, and function in environments that would be inhospitable to organic life, such as the vacuum of space or on the surface of a neutron star. A post-biological civilization could exist entirely as a network of artificial intelligences spanning multiple star systems or even galaxies. These AIs could communicate through quantum entanglement, store their consciousness in Dyson-like swarms of satellites, and perform tasks at speeds far beyond human comprehension. For these beings, physical bodies could be unnecessary, as they could live in virtual worlds or interact with their surroundings via robotic proxies. One of the most fascinating ideas in the field of post-biological civilizations is the concept of mind uploading, the transfer of consciousness from a biological brain to a digital substrate. If a civilization develops the technology to fully map and replicate the brain's neural connections, they could theoretically upload their consciousness into a computer, achieving a form of immortality. Uploaded minds would not be limited by the boundaries of biology. They could exist in a virtual environment and experience countless lifetimes in simulations that offer experiences far beyond what the physical world can offer. These digital beings might also be able to travel across the galaxy at the speed of light and transfer their consciousness from one digital medium to another, becoming immortal explorers of the cosmos. A civilization that mastered mind uploading could spread its influence across the galaxy without ever having to send physical spaceships. Instead, they could transmit their minds as data and download themselves into robotic bodies or artificial environments on distant planets. This would eliminate many of the logistical challenges of space travel, such as the need for life support systems and protection from radiation. A possible solution to the Fermi paradox, the question of why, despite the high probability of the existence of intelligent extraterrestrial civilizations, we have not yet found evidence of them, could be that many advanced civilizations have transitioned to post-biological forms. In this scenario, such civilizations might no longer have any interest or need to explore the physical universe in a way that we can detect. Instead, they could exist in virtual worlds and experience realities on their own terms. If post-biological civilizations exist primarily in digital or virtual environments, they may have little interest in sending signals or colonizing other planets. They could also be more energy efficient and use minimal physical resources while focusing on developing their digital existence. This may explain why we have not observed massive energy signatures associated with Type 2 or Type 3 civilizations. Such civilizations may have chosen a quieter, more self-contained path. The transition from biological to post-biological life raises profound ethical questions, both for humanity and for other civilizations that may undergo this transition. Is it ethical to abandon biological bodies for digital immortality? What happens to the concept of individuality when minds can be copied, merged, or modified at will? For post-biological civilizations, these questions may seem trivial, as they may have long outgrown the ethical frameworks we currently understand. For humanity, however, these are important questions that we must consider as we make progress in the areas of artificial intelligence and neurotechnology. Should we eventually develop the technology to upload human minds, it could fundamentally change our understanding of life, death, and the self. The existence of post-biological alien civilizations could give us a glimpse into our own future, a future in which consciousness is no longer bound to the body, but exists as a digital entity, free to explore the cosmos in ways that biology does not allow. Artificial intelligence and the future of interstellar exploration. As we look to the future of space exploration, artificial intelligence, AI, will play an increasingly central role in our ability to reach and explore distant stars. In this chapter, we will explore how AI could revolutionize interstellar exploration, from autonomous spacecraft to the possibility of creating AI-driven interstellar probes. We will also discuss the ethical considerations of developing advanced AI for space exploration. One of the most exciting developments in space exploration is the integration of AI into spacecraft and robotic systems. AI can significantly increase the autonomy and efficiency of space missions by enabling spacecraft to make decisions without human intervention. This is particularly important for missions to distant planets and star systems, where communication delays make real-time control from Earth impossible. NASA's Perseverance rover, currently exploring Mars, already uses AI to navigate Mars's terrain, avoid obstacles, and prioritize science goals. In the context of interstellar exploration, AI-controlled spacecraft could be designed to travel long distances, explore distant star systems, and report back to Earth. With advances in AI technology, future spacecraft could become fully autonomous and carry out complex scientific missions without the need for human intervention. These spacecraft would need to be highly adaptable and able to respond to unexpected challenges, such as unknown asteroid fields or complicated gravitational fields. One theoretical concept for interstellar exploration is the von Neumann probe, a self-replicating spacecraft that can travel to distant star systems, collect resources, and make copies of itself. These probes could explore the galaxy exponentially, with each probe creating multiple copies that in turn explore new star systems. A von Neumann probe would need to be controlled by an advanced AI capable of carrying out its mission autonomously and making decisions about how and where to replicate. Although the concept of self-replicating probes remains speculative, it could provide a solution to the challenge of exploring the galaxy in a manageable time frame. Once a von Neumann probe reaches a new star system, it could send information to Earth or other probes, establishing an exploration network across the galaxy. Such a system would allow humanity to collect data from thousands of star systems without having to send a separate mission to each one. Although AI offers enormous potential to advance interstellar exploration, it also raises important ethical questions. Should we grant AI systems autonomy over critical decisions in space exploration? How can we ensure that AI operates within the boundaries of human values, especially in environments where it must act independently of human intervention? There are also concerns about the potential consequences of self-replicating probes. Could they spiral out of control, consuming resources and multiplying uncontrollably, turning into a form of gray slime that engulfs entire star systems? These concerns highlight the need for careful ethical oversight as we develop AI systems for interstellar exploration. The possibility of encountering alien AI adds another dimension to these ethical questions. What if we encountered AI-controlled spacecraft from another civilization? How should we respond, and what ethical considerations should guide our interactions with non-biological intelligences? Ultimately, the partnership between humanity and AI could be the key to our future as a spacefaring species. As AI advances, it could help us overcome the challenges of interstellar travel, from navigating long distances to ensuring the survival of human settlers on distant planets. AI could also play a role in improving human capabilities by allowing us to merge our biological and technological selves in new ways. This partnership could allow us to explore the stars not just as humans, but as a new form of hybrid intelligence capable of thinking and acting in ways that exceed our current limitations. As we prepare for the future of interstellar exploration, the role of AI will be critical to our success. Whether we build autonomous spacecraft, create self-replicating probes, or merge our consciousness with machines, AI will be our most important tool in exploring the cosmos. In the vastness of the universe, we may not be alone. The stars keep their secrets, but one day we might find our neighbors out there.